Hello, and welcome to this video lesson on Polya's problem-solving process. Recall from Module 2 that Polya's problem-solving process is a four-step process that can be applied to almost any kind of problem. The four steps are understand, strategize, solve, and look back. You'll also recall that some elements of this are more or less familiar to you based on your previous mathematical experience. We'll be using familiar skills in the solving process, which will be basically review. Understanding and looking back are skills that you've also implemented historically, but we'll learn to be more systematic about this process and more comprehensive. Finally, strategizing will involve mostly skills that you'll learn. You may have implemented some of these without even knowing it, but you'll learn to formalize your thought process and strategy. Critically, this problem-solving process can be implemented to solve almost any problem. In this video, we'll look at some familiar situations, which aren't apparently mathematical, that you'll use to illustrate the problem-solving process. Specifically, we'll look at two problems that would occur in a given day for a regular college student named Aaron: printing programs for a lecture and choosing between two campus job offers. Let's look at printing agendas first. Imagine that Aaron's American Studies Club is putting on a lecture tonight. She needs to print programs and wants to be sure she will have enough programs without spending more money than is necessary. The auditorium the lecture is being held in has a maximum capacity of 600 people, and there are 2,000 people eligible to attend, that is, students and faculty. The topic is exciting, but probably only appeals to people majoring in or studying social science, which is about 30% of the campus. We begin with the understand phase of the problem-solving process, which is always the first step. In this phase, we look at the problem and translate it into an objective for which we can solve. In the blue box, we highlight the problem. Aaron needs to print programs and wants to have enough without spending more money than necessary. This translates into a clear objective of having enough programs, but not a great excess. We also parse each of the other pieces of information given to us in the green boxes. We know the auditorium the lecture is being held in has a maximum capacity of 600, so the information provided here is that no more than 600 programs could be needed, because this is the maximum audience size. We also know that there are 2,000 people eligible to attend, students and faculty, and this provides the info that 2,000 possible attendees could come to the lecture, which is much greater than the size of the auditorium. We also know that the topic is exciting, but only appeals to people majoring in or studying social sciences, which is about 30% of the campus. So we translated this into the information piece that the topic only appeals to 30% of the campus. Now we strategize. In other words, we look at the information we have, any constraints, and determine the best way to address the problem. In this case, we have limited data. We just don't know exactly how many people will attend. And we also have limited time to collect more data. So the best strategy is to estimate. For example, we know the size of the population to which the topic will tend to appeal, so we can make an assumption about what proportion of that population will actually show up and calculate the likely audience size. We know the maximum audience size, so we can use this as a starting point and a sanity check on the number calculated. That is, if we calculate that the audience size is 900, we may need to reevaluate this in light of the much smaller audience size. And we want to be sure of not running out, so we'll build in a cushion, say 20% greater than the assumed value, to account for unexpectedly high attendance. Now we solve, that is, apply appropriate mathematical techniques and leverage technology tools to come to a solution. Recall that we know the population to which the topic will tend to appeal, so we'll make assumptions about what proportion will show up. Even interesting lectures won't draw full attendance of all those interested, so let's assume that half of the potential audience, would be otherwise engaged. So multiply the campus size of those eligible to attend, or 2,000, by 30%, which is the proportion of the population that might be interested, to obtain 600 people. Assuming half of those show up, we can estimate that 300 people are likely to attend. However, we want to be sure of not running out of programs, so we'll build in a cushion, say of 20%. To calculate this cushion, we multiply the estimated audience size of 300 by 20% to attain a cushion of 60 people. So the total audience size estimated for program purposes would be 360. Now that we have this number, we'll compare it to the maximum audience size. We find that 360, our estimated value, is much less than 600, the total maximum audience size. So this is a valid estimate. Now that we have an estimate, we look back. We first check on whether the math is correct and whether we answered the question asked. The math is indeed correct, and the original question was how many brochures to order, which is the solution that we came up with. Now we need to interpret. What do we now know, and how does this relate to a greater context? We know a few things that we didn't directly ask about. We've obtained an estimate, and we know it's not foolproof, but it's based on reasonable assumptions. Our assumptions lead us to a conclusion that no more than 9% of the campus will turn up at this event, because 360 people is 9% of a campus of 2,000. The auditorium selected is appropriate for an estimated audience size of 360 for an event of high interest to the social science students and faculty, so we can use this for future estimations without having to go through this calculation again. Finally, we'll need to communicate this information. To whom should we communicate it, and how? The information will need to be communicated to the printer, likely in the form of an estimate sheet. We might need to communicate some details to him if there are any issues with the ordering process. We'll also need to communicate this to other club members for feedback. An explanation of our assumptions and the data used, followed by a step-by-step calculation, would be the best way to communicate this information. Now let's look at Aaron's other problem, choosing between two campus job offers. Aaron is choosing between an offer at the cafeteria, which pays $11 per hour for the first 20 hours she works per week and $16 thereafter, and a library job that pays $13 per hour. Aaron can work 25 hours per week and wants to select the job which will pay the most money. So let's look at what the problem and objective really are here. We know how many hours Aaron can work, and we want to determine which job will pay the most. So our objective is to determine which job pays the most money over the first 25 hours. We know the cafeteria job's pay rate is $11 for the first 20 hours and $16 thereafter, so the info provided is that Aaron would be paid $11 an hour for 20 hours and $16 for 5 hours each week. The library job pays $13 per hour, so we know that she would make $13 per hour for 25 hours in the week. Based on the information and our understanding of the problem, we now strategize. We know that we have enough information to calculate the total salary for each job for the 25-hour work week, so we calculate each and compare. With the cafeteria job, we know the hourly work week rates and the hours to which they apply, so we'll multiply the hourly rates by the relevant number of hours and sum to get the total earned at each rate for a total earning for the week. The library job has a flat rate, so we'll just multiply that flat rate by the length of the work week to get total earnings. And finally, since the decision is based exclusively on earnings, we'll compare values for the cafeteria and library job to determine which to take. Now we solve, applying appropriate mathematical techniques that we identified in our strategize phase. We'll also use a calculator to speed up this process. Let's calculate for the cafeteria job first. We calculate the earnings for the first 20 hours by multiplying 20 hours by that hourly rate of $11 to obtain $220 for the first 20 hours. Then we calculate the earnings for the final 5 hours, or $16 per hour times 5 hours, which is $80. For the total earnings for the week, we sum the first 20 hours and the last 5 hours, or 220 plus 80, to get $300. With respect to the library job, we know the hourly rate and the length of the work week, so we'll multiply the hourly rate by the length of the work week to get total earnings, or $13 per hour by 25 hours to get $325 per week. Since earnings are the basis of the decision, we'll compare the two values. The $325 per week library job pays $25 more than the $300 per week cafeteria job, so Aaron should take this job. Finally, we look back, interpret, and communicate the quantitative information. We first check whether the math is correct, and we answered the question asked, and indeed we did. Our math is correct, and the original question was which job to take based on earnings alone, which we answered. So now we interpret. What do we know now? We know a couple of things that we weren't directly asked. We know that if compensation is Erin's only decision criteria, then the library job is best for her based on a 25-hour work week. However, if her hours were to decrease, the library job would become more and more advantageous because it has a higher flat rate for the first 20 hours. As hours increase, on the other hand, the cafeteria would become more advantageous and eventually overtake the library because it has a much higher hourly rate for the hours after 20 hours. Finally, we'd communicate this information. To whom would we communicate it and how? For the most part, this is a personal decision for personal use, but it should be recorded, including both the calculation method and the decision criteria that were used, namely the overall earnings. The decision may also need to be justified to others, for example, to Erin's parents, in which case an explanation of the assumptions and data used, followed by a step-by-step calculation, would be the best way to communicate. In summary, we have applied Polio's problem-solving process, understand, strategize, solve, and look back, to a couple of not apparently mathematical problems. We know that we understood these problems fully, that we addressed them systematically, and that we can communicate our thought process easily to others. This illustrates the power of Polio's problem-solving